All right. Let's talk about naming compounds today. So, we're going to start. First things first, I need to check your syllabus. Okay, good. Our first exam is not till next week. Okay, good. All right, we'll see how far we get. Okay, cool. Naming compounds then. Let's talk about it. So, here we go. We're going to see that we kind of have two main classes of compounds. Those would be ionic and covalent compounds. Easier one for us to describe is that covalent or molecular compounds, whichever way you want to call them, those are made of nonmetals only. We're going to see that ionic compounds are made of ions, which are generally have a metal involved, whereas covalent ones must be nonmetals only. So we're going to see that when we name these things, that's kind of our first category. We're also going to have acids later on, which are special covalent compounds. But we'll talk about those at the very end. So we'll start talking about ionic compounds and how to name those. And then we'll talk about covalent compounds, how to name those. And then we'll talk about acids and how to name those. So we're going to have a bunch of rules. But there's really three classifications. So ionic compounds, covalent compounds, acids. And how are we going to distinguish those? Ionic compounds are made of ions. And very often, one of those ions will be a metal. A metal being a positively charged ion species that is part of our compound. With ionic compounds, we're going to see that we have kind of simple ions, like lithium or calcium or oxygen. And we have polyatomic ions, which hopefully by now you'll know, like chlorate and acetate and carbonate and ammonium. Whatever, we have all sorts of different polyatomic ions, right? We have that whole chart. So simple ions, monoatomic, one atom. Those take their preferred charges, or in the case of transition metals, one of many charges. And then polyatomic ions, which have multiple. There are many different polyatomic ions that are fixed. So they all have a specific formula and a specific charge. So let's look at compounds just that are of simple ions first. Our absolute favorite ionic compound is this one, which we know how to name. We call it sodium chloride. We already know that name, yes? Let's look at that. The sodium in this name comes from sodium ion, which is this guy. Positive ions don't change their name. So sodium, when it loses its electron, becomes a sodium ion. No name change. We're going to see this "ide" ending means a negative simple ion, or a simple anion, you could say. We're going to see that anions have this ending "ide." Simple ones, so ones that are one atom only. This is the chloride ion. And that comes from chlorine, which is Cl, Give it an electron, it becomes Cl-, which is chloride. So we're going to take the last syllable of your element name if it's negatively charged, and you're going to replace that last syllable with "ide." So fluorine becomes fluoride, nitrogen becomes nitride, oxygen becomes oxide, hydrogen becomes hydride. The "ide" ending tells us it's a negatively charged ion. And so, these aren't too bad. You just say the names of the ions. If we're just naming things. We'll talk about how to get these formulas in just a second, but right now let's focus on going from formula to name. For these compounds, it's quite simple. And let's do another one. Okay. For a simple ionic compound, their names are as simple as they are. Say the name of the positive ion, followed by the name of the negative ion. And that's in fact the order that we're going to put them in their chemical formula anyway. So it'll be nice and consistent there. So you'll want to definitely have your periodic table on hand for these, because you probably may not be familiar with every single one of these elements, but I don't have time to waste on finding all of them, so we're just going to go for it. So Ba is barium. And we have the negative ion here is chloride. So again, that comes from the word chlorine. Because it's the negative one, it's the second one here. We always put positive then negative. Or negative one, it changes the ending to "ide." This one would be sodium phosphide. And then lastly, we have lithium oxide. And so we see here there's a definite pattern, right? We say for simple ionic compounds, we say, aha, the name of the cation, we'll say, followed by the name of the anion. 2 parts. Positive ion, negative ion. Positive ion's name doesn't change. We just say barium ion, sodium ion, lithium ion. Positive things don't change. Anions do take the "ide" ending. So instead of chlorine, it's chloride. Instead of phosphorus, it's phosphide. Instead of oxygen, it's oxide. So simple ionic compounds follow this very nice pattern here. We're going to see if something has variable charges. Actually, all ionic compounds have this pattern. It doesn't have to be simple ones. We're going to see that complex ones still follow this pattern. If we have, for example, we can't go into that yet because we have to talk about charge balancing. Never mind. Let's talk about some with polyatomic ions now. We see here, no, I've got to talk about charge balancing first still even to do this, so let's do it. Okay. Let's say we have, let's do potassium bromide. If we want to take the name and go into the chemical formula, we're going to need to know a bit more information, or we're going to have to think about it a little bit more. Going from formula to name is a little bit easier. Going from name to formula is a little bit harder. So this tells us, the name tells us the name of the cation and the name of the anion. So potassium ion, K+. The bromide ion is Br-. And so now what we need to do is figure out how many of each of these we need in our formula. And we can say, oh, well, they're of the same charge, magnitude, but just different sign. So we just need one of each, and the charges will cancel out. And indeed, that is the case. We're going to see they have the same charge, so we can just stick them together. But we're going to see sometimes we need multiples. Important thing to note is all compounds are always neutral. Or one way to describe that is that they are charge balanced. So, Oz, what are you doing? In this case, the charges are the same but opposite. That makes a lot of sense. They are the same magnitude but different signs, plus and minus 1, so they can just cancel each other out. But if we have something like potassium sulfide, well, the potassium ion is K+. The sulfide ion is S2-. Remember, sulfur in group 6 prefers a -2 charge. So if we put this together, we get Ks-. Well, that's not right, because compounds have to be neutral. So we need to revisit this and be like, aha, well, if we have a sulfide ion that's -2, well, we're going to need, in fact, 2 potassiums to balance that out. So we would say, we need K2S here. We need 2 plus 1 times 2, because here we have -2 times 1. Oops, not -1. We need these to be the same but opposite signs. So we need these to be charge balanced. We can see here, I mean, it's not terribly difficult, that we need 2 potassiums to balance the sulfur. Gotta balance them properly. There is a shortcut to this, oops, which is nice and easy. If we have our ions, what we can do is crisscross them. Be like, aha, well, this 2 and this 1 are going to end up becoming the new subscripts. That becomes K2S. So you can take your charges and just crisscross them, turn them into subscripts, and you'll be able to charge balance your compound. You can take the charges and turn them into subscripts for the other ion. So the S2- and the K+, we can just crisscross those, and now we have K2S. Or we can think about it and be like, well, okay, we have potassium, which is +1, sulfur, which is -2. We're going to need 2 +1s to balance out the -2, so we need 2 potassiums. Either way will work. How about another one? Let's do magnesium oxide. Again, we're going to need to recall that magnesium is Mg2+. Hi, Oz. An oxide is O2-. Again, just looking at their preferred charges. If we try and crisscross them, we get... Oops. No, I don't need whatever that is. If we try and crisscross these, we get Mg2O2. But if we were to just look at these and go, well, they have the same charge but opposite sign, we just need one of each. We just need one of each of these to balance it out. And indeed, we're going to see that this is the better option here. We're going to see that we always represent ionic compounds as empirical formulas, meaning that we have the lowest ratio possible. So it doesn't make sense for us to say Mg2O2 because each unit of this compound is really just one magnesium, one oxygen. To say Mg2O2 means that there's some complex relationship here that necessitates, like, the smallest unit we could make is Mg2O2. But that's not something we're going to have to worry about here. So we're going to see, for us, we're going to have one name for one compound and one compound for one name. So things are going to be nice and easy for us. We can't say both of these are magnesium oxide. Seems silly that way, so this will be the best way. So, actually, let me write that again. We need to reduce this to MgO because both of those are divisible by 2. Technically, yes, we could put 2 of each together and it would work, but we always represent ionic compounds as the empirical formula. Remember, empirical means the lowest ratio. Between those two. So we're going to display it as that. All right, so if you are going to use this crisscrossing method, that's great. Just pay attention. If you have subscripts that are divisible by something, by the same thing, you'll want to reduce it if possible. All right, so far so good. Let's do another one. If any questions come up, just put them out. We have this like arrival of 5 chihuahuas into the room. They've just all decided to come in at once. Whatever. I was like, what's happening? All I hear is tip tap, tip tap, tip tap as they're coming in. All right, here's another one. Calcium nitride. If we have been good in our studying our preferred charges, we'll know that calcium ion is 2+, the nitride ion is 3-. If we crisscross these, we get Ca3N2. You can get that from crisscrossing. Yeah, it really is the Chihuahua takeover. Have you guys met this one yet? Oh, you're getting chunky, mister. This one is Gumbo. He lives for food. That's all he ever cares about. So he just wanders in, looks for food, and then leaves, usually. Hi, little dude. You're going to go look for food. You're going to do a little dance. Yay. Okay, there you go. That's Gumbo. This one is Oz. Oz has his tongue out on the other side as Gumbo. Oz is apparently Gumbo's father. Or so the shelter said. But we'll see. Though Gumbo always steals his food, so Gumbo is a little bit chonky. And then Rooney is over there, but he doesn't like to get picked up, so we'll leave him on the floor. So, maybe he's going to let me. Are you going to let me pick you up? Yes, he is. This is Rooney. He's a little squirmy. He only has one eye, and he's pretty grumpy. But, that's him. So this is Rooney. So there we go. All right, there's the... Apparently one of them came in and left, so there we go. There's some of the chihuahuas. All right, back to this. We can also do this... We can crisscross things and get it this way. We can crisscross, and it'll work. You can set your switch your subscripts and charges and just crisscross them that way. Or you can say, okay, well, Ca2 plus N3 minus. I can't say, well, I need 1.5 calciums to cancel out the nitrogen. I mean, you could say that, but that's not the greatest way. The best way to be like, well, okay, well, what's the least common multiple that I can have of these? The least common multiple I'm just showing you several ways of doing the same thing, so whatever works for you. The least common multiple of 2 and 3 is 6, right? The smallest number that's divisible by both of them. And so we'll say, okay, well, we need both of these to be 6 to balance out. So if we have Ca2 plus, we're going to need 3 of those to be 6. And we're going to need 2 of the nitrogens to be 6. And so we're going to put those then as the subscripts. And then we'll end up getting our formula that way. So either way you like to do it. Least common multiple takes a little bit more thinking, but it will get you there without having to worry about reducing your subscripts. Crisscross is faster, but then you always need to double check that everything is not divisible by the same number. So either way you like to do it, I don't care. You may choose. You have the choice to do whatever you like. All right? Any questions so far? All right, I'm going to write our formula down again. For ionic compounds, it's the cation name followed by the anion name. I'm going to show you a couple of other compounds, and I'm going to give you their names, and we're going to talk about them. So, how about... And how about we do... Okay, names of these guys. This one is sodium bicarbonate. This one is potassium perchlorate. And this one is magnesium acetate. So notice with these polyatomic ions, their names are exactly identical to what they are on the chart I gave you, right? So their names don't change. We had to change the name of simple negative ions, but for polyatomic ones, their name is already determined for us. For example, bicarbonate is HCO3 minus. And that name is fixed. We don't make it bicarbonide or anything. It's bicarbonate. So polyatomic ion names do not change. And we're going to see, we have a nice example here where we needed 2 of this polyatomic ion to balance. For example, if we had previously magnesium chloride, well, that's Mg2 plus and Cl minus. If we crisscross those, we get MgCl2. With magnesium acetate, It is also a 1 minus ion. So if we crisscross, we need 2 of those too. But the problem comes if we just write it that way. Now what have we done? Well, we now have 22 oxygens, right? So that's not good. So what we do is we put parentheses in. And those parentheses tell us that subscript 2 applies to the entire parentheses. So this 2 represents 2 of the entire acetate unit. So we need 1 magnesium ion and 2 acetate ions. Put those together and we have balanced our compound. So the 2 goes with everything that's within it. So if I were to ask you how many carbons are in this compound, you would say there's 4 carbons. Right? Because there's 2 acetates. Each acetate has 2 carbons, so we've got 4 carbons put together. Let me put that all together. Alright? So anytime you need multiple of a polyatomic ion, you have to use parentheses. Alright, so let's see another one. How about calcium bromide? Let's go ahead and go from name to formula here. Hi, Rooney. Okay, calcium, easy, Ca2+. Bromide, we have to think about. Bromide, we're going to see that, remember, we have different endings for these. Compare this with calcium bromide. Remember, ide, I-D-E, refers to the negative simple anion. So that's Br minus. Bromide, though, ite is an ending for polyatomic ions. And if we look on our chart, we see, bromide is this ion here. It is polyatomic. And if we want, we have bromate as well, which is BrO3 minus. So we have, unfortunately, things that are very similar sounding. And so that's why we're going to see here spelling is super important. Because if you give someone calcium bromate instead of calcium bromide, they're going to die. So, I mean, you probably wouldn't be giving them calcium bromide anyway, but there are problems. So you don't want to be giving the wrong compound to somebody. And I doubt, you'd have that in your pharmacy ready to hand out to patients anyway, but just in case, it's super important that we get our naming correct, because each compound has its own unique name. So, if we put these together, calcium bromide, we see if we crisscross, we're gonna put a 2 with bromide and a 1 with calcium. Remember, since there's 2 bromides here, we need parentheses. If we do the same thing here, we do not need parentheses because bromine is just 1 element, so we can go ahead and put the 2 directly on it. And remember that 2 is, what's the mathematical word? Commutative? It applies to everything within it. So everything within that parentheses is covered by that 2. So we have a calcium ion, 1 bromate ion here, 1 bromate ion here. So we see we have 2 bromates. I'm sorry, bromides. There you go, I just killed the patient. My bad. So bromide ions, there we have 2 of them. In this one we have the calcium, we have 1 bromide, we have a second bromide. So that's what this kind of looks like. And again, notice these are all the lowest ratio. Okay, let's do another one. It's going to make just a little bit more thinking related. Calcium oxalate. Something you might find in a kidney stone. Oxalate is C2O42 minus. If you crisscross here, I'm using this as an example because I don't want you to go too crazy with your reduction. If you just crisscross this, you might be tempted, well, look at all these 2s and a 4. They're all divisible by 2. These 2 here are part of the polyatomic ion. And those are never to be touched. Do not mess with those numbers. Those numbers cannot be messed with. Alright, because each oxalate is a unit. It comes as a set. So you can't say, well, I'm going to just say put CO2. CaCO2. Is this right? No. Absolutely not. But the ones in green are subscripts from charge balancing. Right? From crisscrossing. And those are to be reduced. So they're both 2. We'll divide both by 2. And so we end up with CaC2O4. We've gotten rid of the second unit, because if we were to draw this out, we'd say, we've got calcium, we've got an oxalate, we've got another calcium, we've got another oxalate. It's easier to just say, well, I just have the one set. And so that's why we reduce, because it's redundant to have duplicates. And so we can only mess with, for polyatomic ions, we can only mess with subscripts outside of parentheses. Subscripts that come from charge balancing. The subscripts that are part of the polyatomic ion, we do not mess with. Those stay the same. Those do not get touched. All right. How are we feeling on those? So far, so good. All of these rules, by the way, are on the chart that I have given you, which hopefully you have found. Okay, where is our chart of fun stuff? Remember way back when I gave a whole chart of good stuff? It's this lovely thing here, apparently. Oh, you guys are not watching the screen because I didn't copy that screen. Oh, did I not give you this fun? It is summary of ions. Okay, cool. Okay, if I pop open this window for us, that's not that window. Let me try again. Okay, all of the rules here are the same, or they're written out here. So the rules for ionic compounds are written here. And so we're going to see we've covered now this kind of first bit here. This is, how to change the simple ions, the anions there. There's some patterns here that you can see. If you memorize all the 8s of everything, all the 8s, for example, even though the 8s may not be related, like phosphate is PO43 minus, and chlorate is ClO3 minus. the relationship from ate to ite is the same. So from phosphate to phosphite, we lose one oxygen and keep the charge the same. For chlorate to chlorite, we lose one oxygen and keep the charge the same. Bromate to bromite, lose an oxygen, keep the charge the same. Sulfate to sulfite, lose an oxygen, keep the charge the same. So in Discord, I'll find it for you. Okay, so where are we here? We do not need the lecture notes right now. If we are in extra resources, it is this one right here. Summary of ions. I will, whoops. Well, that's where it is, and there it is. Okay. Let's react to this so we can see it perhaps. Oh, whatever. Okay. There we go. I'm going to put a poop react. So, apparently it's not going to, but that's where it is. So, oh my gosh, I'm sorry. I'm totally not showing you Discord. Oh my gosh. Sorry. So, on our Discord, right here where it says extra resources, so it'll put you down here at the bottom. We scroll up, we scroll up, we scroll up. We see this PDF here. I'll put it so it's right at the top of the page. That says Summary of Ions. That's the document that I'm looking at here. There's another list of ions somewhere up here. You can use that too, but everything is on this Summary of Ions chart. So that's where that is. Okay, and so that's going to have also your preferred charges for many things. Don't trust the transition metal part on that chart. Just so we're aware of that. That's common common charges. Anyways, back to this. So that's where that chart is. So you can see all the rules are going to be located there. So it's going to be your handy dandy cheat sheet, along with all of the polyatomic ions. All right. So far everything's been pretty simple. But transition metals can take different charges. Right? So what do we do? For example, these are both compounds of iron and oxygen. But we learned that, so far, we have to just charge balance things, and then we get one compound out, and so we have our name calcium bromide, means we have one compound, it's CaBr2, and that's it. But if we take a look at these ugly compounds, I say ugly because fail, right? But we're going to see here that we're going to look at our negative part of this. Look at the anion. That's what we're going to do. We're going to say, okay, well, we know if we have one oxygen, it's -2. We know oxygen always takes the charge of -2 when it's by itself like this, as an anion. So therefore, the iron must be +2. I mean, that makes sense, right? We know oxygen takes a -2 charge, and that's a fixed charge. So oxygen doesn't have the choice. Oxygen always is -2. So therefore, if I've given you this chemical formula, that means that the iron is +2. And we would therefore write this in the following manner. We're going to write it as iron, which is Fe, 2 oxide. We put here the charge of the metal. And this is only for metals that take variable charges. So something like calcium, you don't need a 2 there, because calcium only takes 2. But iron can take multiple charges, because it's a transition metal. And we'll see even some of the like lower down, like lead or tin, can take multiple charges as well. But we're really going to focus on transition metals here. So, iron 2 oxide. All right. If we look at the second compound, we know that this part must be 3 times -2. We have 3 oxygens. Each oxygen is -2, which is -6 overall. So that means overall, this must be +6. And if we have 2 things, each one's +3. I'll show you another way to look at that. This one we would call iron 3 oxide, because the iron is +3. If we want, we can do this here. That's also the charge of the metal in that case. If we take a look at the second one way to think about this, we could say, okay, well, we've got 2 irons and 3 oxygens. We know that that has to be neutral. They cancel out. There's no charge overall. We know that oxygen is -2. Doing the math, 2 irons -6 equals 0. So 2 Fe equals 6. Fe equals 3. Or more specific, +3. And so we can get the charge of the metal that way if we want to just do a little bit of algebra. So, or we have a faster way. We could also, if we could crisscross to get subscripts from charges, we could get charges from subscripts by doing the opposite. Anti-crisscross. Put them up here. And now we get Fe 3 plus O 2 minus. So, multiple ways again. Choose whatever you like. Whatever you like, it will work. And so as a result, we know that Fe3 plus is iron 3. That's the name of that ion. And the oxygen 2 minus is called oxide. So that's our name. Okay, so the anion will help you determine the charge of the cation if it's got a variable charge. So only positive things can have variable charge. All of our negative ones are fixed. So we're going to look at the negative ones because those are our like dependable ones. These pesky transition metals do all sorts of weird stuff, so who knows what's going to happen there. However, as with before, you see this algebra way takes a little bit more time. It will always get you the correct answer, though. The reverse crisscross, while faster, again, you're going to have to keep things in your mind. You have to remember things if you're going to do the reverse crisscross. For example, we have this compound CrO3. Reverse crisscross. We get Cr3 plus O minus. Remember the subscript of the chromium there is 1. If we reverse crisscross, we take the subscript and give it as now a charge. Aha, but. We do not have O minus, do we? So, you have to multiply everything by 2 to get it to O2 minus. So that tells us that we really have O2 O2 minus. So we need to multiply our other one by 2 to get 6 plus. And indeed we see CrO3, 3 oxygens, 3 times -2 is -6. We have 1 chromium to balance that, so that chromium must be +6. So again, you can use algebra and not have to worry about this part about it, about double checking yourself. So this is the opposite of the reducing thing, right? So at some point, if we were to just take these, we'll get Cr2O6. And someone said, aha, well, those are both divisible by 2. Reduce that to CrO3. So, again, both methods come with their set of drawbacks. Algebra takes a bit more time. Crisscross, you have to double check yourself. Right, make sure you're not getting ions that don't exist. So we can't have something with O minus. It has to be O2 minus. And so naming this compound, you'll get chromium 6. How do I spell chromium? There we go. Ooh, I guess we need to go over our Roman numerals just in case. It's been a while since we discussed these with Roman numerals for our charges. I'm just going to give you 1 through 10. We're not going to ever have something 10, but whatever. These are the Roman numerals. These are your Roman numerals from 1 to 10. So we use the Roman numerals for variable charge metals. Okay. Whew. And so remember, that tells us the charge of the metal. Let's do this one. Let's go from name to formula. Name to formula is always the easier one, right? Oh, no, it's not. For this part it is. For the transition parts it is. Because Cobalt 2 tells us we have CO2+. Hydride is H-. Remember, hydrogen can be either plus or minus. The "-ide" ending tells us it's minus. Remember, "-ide" only goes with negative things. So if we need to crisscross these, we get COH2. And if we have, say, I don't know, how about titanium 4 sulfide. Well, that is Ti4+. Remember, the parentheses number tells you the charge of the metal. Sulfide is S2-. If we crisscross these, we get Ti2S4, which we're going to reduce to TiS2. Or you can just say, oh, well, clearly the charge of the titanium is twice as big as sulfur, so we're going to need 2 sulfurs. Again, either way. We can do these with polyatomic ions too. Why not? Let's have vanadium 5 sulfate. Vanadium 5 V5+. Sulfate SO4 2-. This is why I wanted you to have these memorized, because if you're going to have to take a look at where the hell sulfate is on this chart, it's going to take you some time. So you don't want to be wasting time looking at that sort of thing. So I guess it's too late now, but yeah. If we crisscross these, we get V2 SO4, 5. Don't forget you'll need your parentheses here because now we have multiples of one polyatomic ion. Alright, so it's merely a matter of practice. You're going to have hundreds of homework problems on these, but they're fast. You may be tempted to cheat on this homework because there are so many of them. And if you do that, that's your choice. But if you do it properly, you will become a master of naming things, and you're going to be so quick on your exam when it comes to naming things. And that's going to be such an important skill. So, how are we feeling? The only thing different here is now we have things with variable charges. The only thing you need to do is potentially figure out that charge. Let's do one more on this before we look at our next class of stuff. Cocoa 3. Well, cobalt is a transition metal. So we need to determine its charge by looking at the anion. We see, oh gosh, what the heck is this thing? CO3. Well, it must be a polyatomic ion, right? We have multiple atoms there. What's CO3? Well, that's carbonate, which is a 2-. We have one carbonate, and we have one cobalt, so therefore they have to have the same charge. So our cobalt here must be 2+. And so we need to call this Cobalt II Carbonate. All right. These take practice, a lot of it, so keep that in mind. These are going to take practice to get through. So, one more last bit about ionic compounds is sometimes ionic compounds, they crystallize with water. And it's a bit weird to say, but, we might think about, crystals alternating sodium chloride, sodium chloride, sodium chloride, right? Sometimes water molecules get trapped in there, and they are kind of fixed in there. And so sometimes they include them, and those are called hydrates. And they can kind of affect the color of things, and they're part of the compound. So, for example, you might see one that looks like this. This is a very common hydrate. The crystal structure of this compound includes 8 waters for every unit of BaOH2. And so it's just part of it. As it solidifies, it traps 8 water molecules in for every unit of barium hydroxide. I'm sorry, BaOH2. Oh, I gave it away. Oh well. I'll tell you the name of this thing. Since I just did, barium hydroxide is the ionic compound part. And then if something is a hydrate, we just need to see how many waters it has. So we might call this barium hydroxide octahydrate. Octa meaning 8. We're going to talk about those prefixes in the next bit. So for right now, I'm just going to say octa is 8. Leave it at that for now. Something like this would be Cobalt II Chloride Hexahydrate. And we're going to see sometimes certain hydrates I mean, certain compounds can have all sorts of different hydrates, so it's just a way of talking about how many are on it. So, okay, let's take a look at our good friend Wikipedia. I'm not making these things up. Well, I might be. Oh, it's good. Okay, so Cobalt Ii Chloride. Notice it does have the Roman numerals. Again, I'm not making these things up. In this particular compound, there's many different hydrates that are available. And so they have different colors, which is interesting. So the hexahydrate form is this magenta. The anhydrous, meaning there's no waters on it, is this pale blue. And so, yeah, we're going to see that there are properties about this. So cobalt chloride hexahydrate would be this. It's got this dot here and 6 waters. Okay. Apparently the dihydrate is purple. And they're calling this pink. I don't think that's pink. That's magenta or burgundy. But that's besides the point. So the point is that many compounds come as hydrates. There's potentially multiple hydrates per compound. It just depends what you have. And so when you're weighing things out, for example, it's important that you know how many waters are stuck in your crystals, because that's going to change the mass that you weigh out. So those are important too. Okay. So let's move on then. Let's talk about covalent compounds. These are non-metals only. And it's very important that we make the distinction that these do not have charges. Our compound CO2, which will be our kind of reference compound for a covalent compound, is made of carbon and oxygen, and that's it. The name for this is called carbon dioxide. We have heard this name before. There is no carbon 4 plus O2 minus business here. No. These are not charged. These are what we'll see as covalent. They're sharing electrons. They're not being taken away. Whereas in sodium chloride, the chlorine has taken an electron away from sodium to become a negative charge, and the sodium is now positive. With these, they're sharing electrons. They're not charged. So these do not have charges. We have, therefore, a different way to name them. Giving you a bunch of examples here. There's no way to salvage this one. Okay, let me try again. Dicarbon trioxide. Hopefully here we're seeing a pattern. We're really lucky with covalent compounds. They're the easiest ones to name. Where you'll have prefix, first nonmetal, and then prefix, second nonmetal, with the "ide" ending. It's very simple like that. One rule for us is we never start with mono. So, CO, we do not start with mono. We don't say monocarbon monoxide or monocarbon dioxide. It's assumed, if we don't say any prefix, that it's one. But we do need to include mono for the second one. So unfortunately, we don't say carbon oxide. We have to say carbon monoxide. All right, so we don't start with mono. Mono can't be part of our first nonmetal, but it can be part of the second one. Here are our prefixes from 1 to 10. So, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So, you'll want to learn these as well. Many of these you'll see are familiar, like hexagon. You've heard that before. Hexa means 6. Octagon, 8. Octahydrate, 8 waters. Tri, 3. Maybe the only one new is tetra, and maybe nona and deca. The rest are probably in your vocabulary already. So, yeah. Let's do another one. CCl4, we would call this carbon tetrachloride. The pattern is simple. Name the first one with how many it is. Name the second one with how many it is. Ta-da! And you're done. Let's do one more. P2O5, we'll say diphosphorus pentoxide. One thing to know, a lot of these do have oxygen in them. Oxygen is a very common element to include with these compounds. These prefixes, they lose their A before oxide. So we don't say pentaoxide, we say pentoxide. So that's just one more thing to keep in mind. So we can say dioxide, that's okay. But we would say tetroxide. We don't say tetraoxide. Just for flow of how it works. But we would say something like triiodide. We don't mess with anything but with oxygen. So with oxygen, we just get rid of the last A. So octoxide. It's a little weird. Heptoxide. However, we can have multiple I's in a row. That's not a problem. It's just A before O we don't do for some reason. So the oxide, we drop the A if it's part of the prefix. Let's do a couple on the other side. Let's see, how about I think this particular set, taking a covalent compound name and turning it into the formula, is the easiest part of all. As long as you know the symbols of the elements. Boron tribromide, BBr3. It tells you exactly what elements to put and as well as what those subscripts need to be. So boron is B1, one boron atom. Tribromide means Br3. Stick them together, you're done. Easy as that. Phosphorus pentachloride. PCl5. Easy as that. Do we like this way of naming? I do too. It's the easiest way. You just say what elements are there and how many there are. That's it. How about this one? Oh, well, this is simple, right? It's calcium difluoride. Why did I do the angry buzzer sound? I did the angry buzzer sound because it's not a covalent compound. This is an ionic compound. It's an ionic compound, so we need ionic rules. Ionic rules tell us this is calcium fluoride. Chemists are anti-redundancy. We do not like to say the same thing twice for whatever reason. And so this compound is calcium fluoride. You're going to see, unfortunately, it will be very tempting to just say monoditritetra for everything. You can't do that. You can only use it for covalent compounds. Compounds that are made of non-metals only. Calcium is a metal, so we can't use covalent naming rules here. The reason that we need these covalent rules is because look at how many compounds I've made with carbon and oxygen. And I can make more. These particular ones tell us, okay, in this compound I have 1 carbon and 2 oxygens, and that's my smallest unit. That's 1 molecule. The next one I have 1 carbon, 1 oxygen. Smallest unit there. Next one, 2 and 3. So there's different combinations I can make that are all valid. But with calcium fluoride, for example, there's no way for me to put any other combination besides 1 calcium and 2 fluorides. That's it. There's nothing else I can do. So as a result, the name is simpler. The name does not include the number of any of these because there's never any other case that it's going to have besides CaF2. So that's calcium fluoride. Nothing else is calcium fluoride. There's no other calcium fluorine compounds I could make. So as a result, that's the naming convention we use. So we don't need to say difluoride because we already know there's no other way to mix calcium and fluorine together. Even worse, something that'll really make me mad is if you do this. If you do this, I'm gonna take your homework and shred it. This breaks all the rules. Get it out of here. This is like doubly angry. So, don't do that. There's so many things wrong with that name. But believe it or not, people are always tempted to. Because I get it, there are a lot of rules. But if you can identify your type of compound first, if you can say, oh, this is an ionic compound, this is a covalent compound, this is an acid. We'll talk about acids in a little bit. That's the first step. You need to be able to identify from a formula which of those 3 it is. You'll also want to be able to identify from a name which of those 3 it is. So that's the first step. If you can do that, then you'll apply the right rules. And that's how you're going to get everything right, and you're going to get 100% by doing that. So that's the skill you want to do, is you have to be on the lookout for what type of compound you're dealing with. So I think it's useful, even though I don't ask you specifically on your homework, for your own benefit, it is a good idea to be like, oh, well, this is an ionic compound. So I'm going to make sure that I use ionic naming rules for this compound. This compound's a molecular compound. I'm going to use my molecular compound rules. This one's an acid. I'm going to make sure to use acid naming rules. All right, I'm going to introduce acids real quick. And for those ones, they have the most complex rules. So we're going to pick it up again on Tuesday with it, but I am going to have it so that you can at least get to work on your homework. So everything again is on your summary of ions sheet. It's all there. Trust me, it is right here. Summary of ions here. Come on. There we go. All the rules are written here. So if you can identify your compound, it's blank. Oh, there we go. If you can figure out what type of compound you have, the rules are here. Ionic compounds, you have a metal that's present, or ions. Tells you how to name it. Covalent compounds, no metal is present. And so you have these rules here. And then finally, acids, we're going to have 3 different rules here. But we'll learn those in just a second. So all of these are written here. Okay, so if you can identify the type, refer to this chart as you're doing your homework, because it's going to be a great way for you to be like, oh, that's right. I'm learning the rules for naming covalent compounds because I've identified as this, and I'm looking at my chart here. Oh, that's the one that uses di-tri-tetra, all those. And so as you do them, you'll get these rules integrated in your head. So as soon as you see an ionic compound, you'll be like, oh, calcium bromide, whatever, calcium sulfate. I get it though. There's a lot going on, hence you're going to have so many problems. The problems are not long, they're very quick, right? And you'll get quicker as you go through it. It will seem overwhelming, it's not, trust me, and you will be happy for it. Okay, let's learn our acids. So, one ion we have I have been very careful to avoid thus far is this guy, or rather hydrogen in general. So we know H- is hydride. That's going to be in ionic compounds only. And it must be paired with a metal, right? Hydride is a negative, so you need a metal which is positive to balance with it. Sodium hydride. In this case, hydrogen is negative. We can have hydrogen in covalent compounds too. For example, HCl. We would call this I gave you the example without telling you the rule, but in covalent compounds, we actually follow ionic rules for hydrogen. We treat the H as H+. The reason for this we're not going to learn for a couple of chapters, but I'm telling you now. In covalent compounds, we are going to act as though it's H+. And so, we actually follow ionic rules for this. So, even though they're both nonmetals, hydrogen is a nonmetal. It's a gas, right? It doesn't have the properties of metals. Hydrogen is actually weird because it does positive things. Hydrogen's strange. But suffice it to say, we follow ionic rules for compounds with hydrogen. So hydrogen chloride. This will be hydrogen sulfide, for example. This one, hydrogen oxide. You might be tempted to say dihydrogen monoxide. That's a little bit less accurate. We very often will use ionic rules with hydrogen compounds. You don't trust me? Nobody says dihydrogen monosulfide. That wouldn't be something if we just look it up. Wikipedia time again. We go here. We get the systematic name. That's the rules we're learning. Hydrogen sulfide. Trust me. This is the way to do it. We're not going to call it sour gas or sewer gas. We call it hydrogen sulfide. And I did that. H Oops, I'm writing on the wrong thing. H2S. I write in our formula, hydrogen sulfide is what comes out. We do not get dihydrogen monosulfide as our name here. So even though you might be tempted with water to say, ah yes, dihydrogen monoxide, that is not systematic. For hydrogen compounds, we treat them as if they are ionic. Isn't that fun? It gets worse. Hydrogen's really going to mess with you. And I've got 6 minutes to do it. I'll tack on a few minutes because I started a little later today. If your H plus containing covalent compound is dissolved in water, it is acidic. And so we're going to name them as acids. So if we take HCl and dissolve it in water, that's what this means. AQ, aqueous, which we abbreviate AQ. We call this hydrochloric acid, a name you've heard before. I'm going to give you a couple of examples, and we're going to then learn the rules, and you're going to be able to start practicing, and then we'll finish this up on Tuesday. This compound, this is not even a covalent compound, this is an ionic compound, and we have H+. We are going to call this Chloric Acid. Hold on, let me close my door real quick. Okay, Chloric Acid. And then the last case of acids we're going to see, this is an example, is Chloric Acid. So, it'll be fun. This is how we do it. Because all of these have H+, so we look at the anion. The anion is going to be what's different, because all of these have H+, right? They all start with H, they all have H+. So, if we look at these three, these are the anions for those three acids. This one, its name is chloride. This one is chlorite. And this one is chlorate. They all have different endings. And we're going to see the rules for these. For "-ide" ending things, it becomes hydroic acid. For example, HBr, which is Br minus. Br minus is bromide. That is hydrobromic acid. Or HI, hydroiodic, acid. Or hydroxyic acid. There's your water again. You could name it as an acid if you want, and indeed hydroxic acid would be how you do it, and that is a technically correct name for water. But that's the idea here. We took oxide, becomes hydroxyic acid. Iodide becomes hydroiodic acid. Bromide, hydrobromic acid. So if your anion ends with "-ide", you get rid of the "-ide", stick the rest of it in that space. Hydroblankic acid. So hydrosulfuric acid, hydroselenic acid. So selenide, selenium. Selenide is the 2- form of selenium. Here, yeah, why not? We'll put that. Hydroselenic acid. That's the pattern. All right, I'm going to just introduce the other two patterns, and then we've got to go, but we'll continue on with this next time. And I'll put your homework up so you'll start practicing. I'll give you a few more skills and practice things as we go on. If your anion ends with ite, you will turn it into us acid. For example, HNO2, nitrite. This becomes nitrous acid. If you have bromite, bromous acid. For example, or what's another ite? How about phosphite? This is phosphorus acid. Sulfur and phosphorus are special. They actually will keep one of their syllables. So these two are kind of special. It's not sulfus acid and phosphorus acid. For whatever reason, these guys are special. So I'll just put a little asterisk on them. But that's what we would call those. All the other ites, though, follow the same pattern where you just take out the ite and put us acid. So nitrite, we got rid of ite. Nitr is left. Us acid, nitrous acid. Last category is the ates. And those are just going to become ic acid. So the examples: HClO4, HNO3, H2SO4. By the way, the number of H's is just however many you need to balance out your compound, right? So sulfate has 2- charge, you need 2 H's there to balance that out. Perchlorate becomes perchloric acid. So everything that's not the 8 gets chunked into that blank spot. Nitrate becomes nitric acid. Sulfate, again, this one's going to be a little bit special. Sulfuric acid. Special case. That one, again, it's not sulfic acid, as we might think, but it is sulfuric acid. That's whatever reason we keep that way. Phosphoric, same idea. This is phosphate and carbonate. Phosphoric acid. Again, that's a special one, and then this goes back just carbonic acid. So, that's all of our rules. We'll get to working on them. Tuesday we'll continue with this, and then we'll start talking about some reactions. That'll be fun. I'll put up your homework either later today or tomorrow, so you can start working on it for this naming stuff. We have someone who wishes to come in. I don't know which doggo it's going to be. It's always a surprise. Let's see. Who do we got there? Come on in. All right. Other than that, any questions? Oh, you're not who I thought. We have Beauregard this time. There you go. So he's here. Hello, hello, hello. He's not a Chihuahua, but what a surprise. Oh, there's another one. Come here, Miss Jersey. And then we've got Miss Jersey again, who is the most likely to interrupt our class with her barking. So there we go. That's your last little bit for today. So you can end on a happy note after all of this work naming things. So there we go. Alrighty, we've done a lot. We are going to start chapter 3 next week. So there we go. Good girl. Okay. Enjoy your weekends, everybody. And I'll see you again on Tuesday. Alrighty. Take care.